Let us look at problem 11.4, where we have a train that couples with a spring and a bumper. So this is the perfect example for a situation where we have change in velocity and a change in displacement. They're telling us that the x, or the relationship between distance and time, or this is going to be our x-axis, the relationship is given by 60 e to the negative 4.8t times sine 16t. Okay, so in real life, they would put sensors and time, very fast data acquisition system in microseconds or milliseconds, and see how much this distance is varying. So obviously, because of the spring, it's going to go front and back, and this bumper is going to help it reduce the amount of speed. Okay. All right, so they're telling us to find the position. So what's x as a function of t? What is the velocity as a function of t? And what is the acceleration as a function of t? And that all has to be done for when t equals 0 and when t equals 0.3 seconds. Okay, 300 milliseconds. So this is the same as 300 milliseconds. But they're telling us that just use 0.3, not 300 milliseconds. The units are in seconds. So be careful with the units. All right, so the first thing is, well, it's pretty simple because we have the function, we have x as a function of t is equal to 60 times, this is a 0, times e to the negative 4.8 times 0, and all this multiplied by sine of 16 times 0. So let's use the calculator, and we will be able to find that if we go to the calculator, we will be able to see that we are multiplying 60 times e to the 0 times sine 0. Okay, so this is a good chance to get to practice. The sine curve, I've been telling you that dynamics is really, it really will take you a long way if you know functions. So sine starts at 0 and will come back at 0 at pi over 2. Then where this is right here, this is 0. So this whole thing equals 0. Okay, so when x 0, we have 0 meters, or whatever unit we're using. All right, so that was pretty simple. Basically what we're saying is that whatever our x point or coordinate system was, when time equals 0, this was at 0. Okay. Now the next point will be for x 0.3 seconds. This is equal to 60 times e to the negative 4.8 times 0.3, all this multiplied times sine 16 times 0.3. Okay, so for this we get to use the calculator. So let's go to our calculator and we'll do we'll do, so go to wolframalpha.com and we'll do negative 4.8. Well, if you have a calculator, you just use your calculator, but I think this will be easier to show you with Wolfram Alpha. And obviously you need internet to be able to use it unless you have the application installed. Okay, negative 1.44. Okay, so this portion right here is e to the negative 1.44 times sine of 16.0 times, well, actually, let's do this first. So what is 16 times 0.03? So 0.3, this is 4.8. Okay, so now what we have to do is multiply 60 times that. Okay, so let's do 60 times e hat, well, this is exponent, negative 1.44 times 4.8. Let's see, 4.8. This is, am I doing something wrong here? Oh, wait a second, did I get negative? So let's see, negative 4.8. Let me do this one more time. Negative 4.8 times 0.3. Yeah, it's negative 1.44. Okay, so what is e to the negative 1.44? 0.23. Okay, 0.23. And what is, so we said that 16 times 0.3 is 4.8, right? Yeah. So what is sine of 4.8? 0.8 negative 0.99. Okay, so 0.996 times 60. Okay, so let's do 60 times 0.23 times negative 0.996. Negative 13.74. Okay, so that is closer, and I think that actually we're missing a bunch of decimal points here. Okay, so that's close enough. Negative 13.74. So when we go to our x of this right here, distance when we have 3 seconds, this is equal to 13.8 milli, is it meters or millimeters? Let me read the problem. Time is obviously in seconds, but this is the millimeters. So 14 millimeters, yeah, it's not very much. 14 millimeters is half an inch. Okay, so 14 millimeters or 13.8 millimeters. Okay, good. So we have the distance at 0 and at 0.3. All right, so now I'm curious, what does this function look like? So we're gonna say 60 times e to the parentheses negative 4.8 times t, and this is sine of 16 times t. So obviously the function is t this time, and we only care from 0 to the right we don't care about negative time, and this is x, really not y, but we don't have to be so picky about what Wolfram Alpha thinks the function is. The variable is t and distance is x, but y, that's also okay. And we're really focused in this part. So if you notice, because of the spring and bumper, it goes back and forth. All right, so now we're gonna need the velocity. Now we're gonna need the velocity. And the velocity will be the derivative, we know this, right, of the distance with respect to time. So the derivative is going to be basically dt of the function, and the derivative is 960 e negative 4.8 times t. That multiplies cosine of 16t, yep, minus 0.3 times sine of 16t. Cool. All that multiplies that. So they're asking us for velocity at 0 and for velocity at 0.3. So let's do that and that. So for velocity at time equals 0. So we have that it will be, when t equals 0, we have 960 times e negative 4.8 times 0 times cosine of 16 times t. Now cosine at 0 is not 0, but this is 0, it means subtracting. So 0.3 times sine 16t. And all this is multiplied by 960e to the negative 4.80 times 0. So t is 0 and t is 0. Times 0 times 0. All right, so let's see what this is. So we said that negative 4.8 times 0. Let's do it again because I need more decimal points. Negative 4.8. Well, oh, it's at 0.3 that I needed. So let's do this, times 0. E to the, what is this quantity? This quantity is equal to, well, yeah, it's equal to 1 because e to the 0 is 1, right? If you plot e to the t, you see that it crosses right at when t equals 0. Let's do when the variable is x. So he knows that I'm trying to plot. When you do x, what's going on? It's not plotting. It's not plot. All right. Okay, well, so in that case, e to the x. There you go. So it crosses at 0 is equal to 1. Okay, that's all I need to see. I don't know why it's not just acting up. All right, but I need to evaluate at negative 4.8 times 0. So we said is 1. Okay, so let's do that like this. To save time, we're gonna do this whole thing at the same time. Okay, so This is 960 times 1. Okay, and this is 960 times, this is where I wanted to check, 0.3, 0.2369. 0.2369 times, okay, cosine of 0 is 1 as well. You can check cosine of 0 is 1. So we have 1 minus, this one will be 0. Okay, and now let's do this. Cosine of 16 times 0.3 is, well, actually, this is 4.8. Cosine of 4.8 is 0.0874. 0.0874 minus 0.3 times sine, it's negative 9961.9961. Okay, so let's do those at the same time. Times equals 0, we'll have 960 times 1, and this is distributed, so 960. And since the distance is in millimeters, we're going to have millimeters per second, right? Millimeters per second. Let me fix that a little, it's too confusing. Millimeters per second. And we know that 1,000 millimeters is a meter, so this is 0.960 meters per second. Okay, so it's almost 1 meter per second. Okay, that's good. Let's do this one right here. V 0.3 is equal to, is just computing this amount of numbers, 960. Okay, so 960 times 0.2369, 227.424. Okay, so this is 227.5, let's say. This is the same thing, 0.0874 minus, this is a plus, 0.3 times 0.9961, 0.3 as well, 0.29. Okay, so we have that this thing plus 0.0874 equals 0.3862. 0.3862 times 227.5. Okay, that's 87.86. V 0.3 seconds is equal to 87.86 millimeters per second. So you can appreciate how in only 0.3 seconds, we have reduced. 0.3 seconds is really not that much. It's only 300 milliseconds. You know, we're talking about less than a second here. It went from 1 meter per second to only 87 to a tenth of that. Okay, so if you approximate this to 1,000, just to show you the powerfulness of a spring in a bumper. 1,000 meters per second, 0.3 seconds later, we're at almost 100 millimeters per second. So all that energy was taken out of the system, and a train is a pretty big system, so that the speed is greatly reduced. All right. Okay, now they're asking us to find the acceleration. And is doing the same thing. It's going to be the derivative of velocity as a function of time, as a function of with respect to time, or the second derivative of the displacement with respect to time. So if we go back to Wolfram and do, actually I thought we did, yes we did, yeah, okay, we did. So what we need to do is do derivative of 960 times e to the negative 4.8 times t. So we're just basically writing out the velocity. Now we're going to find the acceleration by deriving, times cosine of 16 times t minus 0.3 times sine of 16 times t. Hold on a second, let me see. I think that we need to fix this, because this is multiplying that and this is multiplying that. Okay, so 9, I think this is correct, and the answer is, well, it's a pretty long number, huh? Okay, so the answer is E. Wow, actually I'm gonna copy paste this guy. Okay, so this is the derivative. Okay, that is the derivative. Actually the derivative is right here because this is the velocity. Okay, so we need to focus on this part. So they're asking what is the acceleration at time 0 and what is the acceleration at 0.3 seconds. All right, so we're gonna have to do the same thing. So e to the, right, so actually let me write it down because we want to do it similarly. E negative 4.8 times t times negative 13,977 times sine of 16t minus 9216 cosine of 16t. Okay, so when acceleration equals 0, we're gonna have e to the 0 is 1 times sine, this whole thing is 0, minus 9216 times 1. All right, so this is pretty interesting. If you notice, the acceleration is negative 9216 millimeters squared. 9,216 millimeters, so almost 9 meters per second. This is remarkable because that's huge, right? It's quite big, and that's the acceleration needed to reduce the speed from 1 meter per second to 0.1 meters per second, or 1,000 millimeters per second to 100 meters per second. Well, and I know I'm rounding up numbers. It's really from 960 to 87.8, but just to get the concept, that's really what you need to start learning how to see those, how many magnitudes are we increasing or reducing, because that's really what we want to know. Right, so let's do the last one, which is at 0.3. We're gonna do, this is e to the negative, I already forgot what is negative 4, is it 0.23? I think I wrote it down over here. Yeah, 0.2369. Negative 0.2369. So if you do that, negative 4.8 times 0.3. Oh no, my bad. That was the, we have to do exponent. You have to evaluate the whole exponent. Yeah, 0.2369. So yeah, I just wanted to confirm because that would be pretty bad. Yeah, so this is negative, wait, no, positive. This is positive 0.2369. Okay, then we have sine of 16 times 0.3, and that was negative 0.99. You can you can corroborate if you want. Actually, I should do that. So let's do 16 times 0.3. 16 times is 4.8. All right, 4.8. Sine of 4.8 is negative 9961, right? So that whole thing is negative 0.9961. That multiplies negative 13,977. Okay, now we have another negative, and in this case we have 9216 that multiplies cosine of 4.8. And cosine of 4.8 is 0.087. 0.087. All right. So basically, we just have to compute all this. 0.2369 times, we're gonna have something here minus something here. So the first parenthesis is 13,977 times, and actually that is negative times negative 0.9961, and here we have 9216 times 0.087. So that is 3,108. So that is, if you notice, the acceleration went down because the bumper and the spring are reducing the, well, let's see. Actually, we get a positive number here. We got a positive number, so it's increasing. So I apologize. So basically, let's plot this function actually. if we get the second derivative, I thought we had plotted this. Yeah, this is it. So this is it right here. So if you notice, okay, from 0 to 0.5. Nope, that's not how you asked to plot it. Okay. I'm not quite sure if it's gonna let me enlarge, but okay, what I'm getting at is that at 0, you have an initial acceleration. This is negative 9,000, and then it goes positive. Why? Because when you look at the train is going to the right hand side and then to the negative direction, to the left hand side. And since it's already buckled or hooked, and it's going to come back and forth until it completely stops. And then you can see that stopping mechanism right here after 0.5.